to the next.
Welcome to the second day of the IEEE Sensor Array and Multi-Channel Signal Processing Workshop, SAM 2020, organized in Hangzhou, China. It has been fully virtual this year. I'm Ji Guoxi from Zhejiang University, China. It's my great pleasure to chair the second plenary session. The second plenary presentation of this workshop is presented by Anna Scaliona from Arizona State University, and the questions and answer session will be followed. Please prepare your questions. The topic of this plenary is distributed signal processing algorithms for big data analytics, principles and techniques. The presenter is Anna Scaliona. Anna Scaliona is currently a professor in electrical and computer engineering at Arizona State University. She was a professor of electrical engineering previously at the UC Davis from 2010 to 2014, associate professor at UC Davis from 2008 to 2010, and at Cornell from 2006 to 2008, and assistant professor at Cornell from 2001 to 2006, and at the University of New Mexico from 2000 to 2001. Her expertise is in the broad area of statistical signal processing for information networks and intelligent cyber-physical infrastructures. Her current research focuses on the studying and enabling decentralized learning and signal processing for big data and complex systems. Dr. Scaliona was elected an IEEE Fellow in 2011. She served IEEE in many capacities. She was associate editor for the IEEE transactions on wireless communications and on signal processing, editor-in-chief of the IEEE signal processing letters, and is currently senior editor of the IEEE transactions on control over network system. She was a member of the IEEE Signal Processing Society Board of Governors from 2011 to 2004. She received the 2000 IEEE Signal Processing Transactions Best Paper Award, and more recently was honored for the 2013 IEEE Donald G. Fink Prize Paper Award for the best review paper in that year in the IEEE publications. Her work with her student, Ling Li, earned 2013 IEEE Signal Processing Society Young Author Best Paper Award. We are really honored to have Anna Scaliona as one of our plenary speakers of the IEEE SAM 2020, and look forward to her overview on distributed signal processing algorithms for big data analytics. After this plenary presentation, we will have a live question and answer session. Whenever you have questions or comments, please type it in chat. You should do this during the presentation so that we can have a live interaction afterwards. Welcome, Anna.
Hi, everybody. My name is Anna Scaglione. I'm a professor at Arizona State University. I want to first thank very much the organizer for inviting me to give this plenary talk for the 11th SAM Signal Processing Workshop. My talk is entitled Distributed Signal Processing Algorithms for Big Data Analytics, Principles and Techniques. Why distributed learning? In the last 50 years, we have witnessed an exponential growth of network devices. These billions of edge devices are acquiring a lot of new data. And the problem with big data analytics has triggered several ideas for cloud computing. However, this is becoming quickly insufficient. And as these devices become more powerful, the tendency is to leverage distributed algorithms to push the computation towards the edges of the network where the data are produced. There are two different flavors of distributed computing algorithms, and they are tied to the network configuration. The so-called master-slave algorithms adopt a star network infrastructure. The edge of the star are clients or servers or workers, and the center of the cloud is the master. The other very popular configuration is the so-called multi-agent configuration, where nodes instead are connected through an arbitrary network, mesh network, and the structure is completely flat. The objective of this talk is to address the following question. First of all, what kind of problems are amenable to be mapped onto a distributed implementation? And how do these algorithms work? Decomposable problems have a particular structure, which is the first thing I will pay attention to. And then I will move on to explaining master-slave algorithms. Really, those algorithms do provide a necessary introduction for understanding peer-to-peer algorithms or multi-agent algorithms. In fact, the basic observation is that typically, if a problem has a master-slave implementation, it is also amenable to a multi-agent or peer-to-peer implementation. Now, another caveat is that the communication cost for peer-to-peer algorithms is generally higher, but the benefit that they bring is that they have much greater fault tolerance and allow for very lax scheduling options, which are ideal in a distributed environment. The semantics of a decomposable computation are as follows. Each node in the network has a different expression, and that is derived from the data that they acquire or the observations that they acquire of the environment. And the goal is to evaluate in general a function of all of these expressions. You see this index I here that indicates which particular node in the network has access to this expression. The important example that we are going to dwell on in this talk is when we have to evaluate a sum of all the expressions that are available at each node. The goal of the master-slave algorithm is that the master computes the results by receiving the expression evaluated by each slave. Instead, in the multi-agent version, each node of the network exchanges messages with its neighbor, and the goal is to achieve consensus on the result of the evaluation. Let me make two simple examples. The first one is sensors that acquire measurements that are conditionally independent given a certain hypothesis, which is the hypothesis we want to make an inference on. For instance, we could have a canonical test where we have two hypotheses. And in this case, it's clear that the log likelihood of all the sensor measurements can be written as the sum of the log likelihood of the individual sensor's observation. And that would be what we refer to as the expression of node I. A second example is when we want to simply compute the sample mean. And that, in fact, is the optimum maximum likelihood regression in a simple linear model in which we have an unknown parameter theta embedded in IID noise. More interesting though, and that's what most of this talk will discuss, are optimization problems that have a decomposable structure. And it is important to notice is that in this case, we want to typically minimize the sum of expressions that depend on variables of interest. This problem is oftentimes constrained. There can be local constraints as well as coupled constraints that apply to a certain subset of nodes in the network or to every neighborhood of the networks, which is indicated by this calligraphic NI. So for solving decomposable problems like this, the divide and conquer approach comes handy not just in solving inference problem, where the regression problem is formulated as minimizing a sum loss, but also in resource allocation problems where we want to, for instance, minimize the cost or maximize the utility, which would be minus the cost of a certain decision for the network. But let me make a trivial example once again from the signal processing arena. So suppose that we have this simple observation model, again, a linear model, where there is a latent parameter theta common across all the sensor observation. Each is presented through a linear mapping HI, and it's embedded in IID Gaussian zero mean noise. So in this case, we know very well the solution of the maximum likelihood estimate for theta amounts to solving this simple least square problem. And we obviously have a simple centralized solution But what is interesting is, once again, to solve the problem distributedly. And in this case, you see, I want to refer to the expression now more explicitly as a function fi of the unknown parameter vector that we want to estimate. Let me make an example that is more current. The need of training a neural network based on data that are held potentially in mobile devices or IoT devices. And this is a toy example where I want to train a two-layer neural network. This entails finding the weights W1 and W2 and the affine term B1 and B2 for the two layers. Here, ReLU is the simple ReLU activation function, and the expression of the outputs of the neural network is given in here. And you can see that, of course, the output label is a function of the local data DI and a function of such parameters. And the training task is minimizing a sum loss over the mistaken labels. Oftentimes, in combination with the ReLU activation function, we use the cross-entropy the softmax cross-entropy loss function, which is shown here. And so here, the fi of x is simply the term that corresponds to all the sum loss for all the data, the labeled data that are present at a certain node di. And the goal is essentially in training to minimize this sum loss across different platforms. For a resource allocation problem, this could be also a prototypical example. We want to control the power level of several terminals. We want to make sure that the total power over a certain spectrum, which we have divided across this terminal, is no greater than x bar. And so the sum of all the powers across the node has to be below or equal to that value. And we want to maximize the sum capacity, which amounts to minimizing the minus the Shannon entropy expression shown here, where AI is simply the channel gain and WI is the amount of power we have allocated to the particular user. So the former again, the problem again can be cast in this form. We want to minimize the sum of this function, right? So these are the expression, subject to a sum constraint. And the important difference between this and the previous case is that here the argument x is a different x for each of the nodes. And so here we're trying to solve, again, a recursive source allocation problem. Now let's talk about distributed computation. It's very trivial to think how you will parallelize the computation of a sum of expressions in a master-slave fashion. All you need is that each client or edge device transfers the expression to the master, and then the master adds all of these expression up. So it's a one-shot operation. But it's interesting to understand how this type of operation, it's an important primitive that can be generalized to a completely flat infrastructure with the goal of achieving consensus on the average of all the initial values. So suppose we have an expression that we want to evaluate is the sum of some expressions, and let's initialize the vector yi as being the expression that is the initial state value for each element in this network. The idea of the so-called average consensus protocol is essentially to replace the sum across all network, which will be allowing to evaluate the expression in one shot, with repeatedly taking convex combinations of the current states of the system and replacing the new state with these convex combinations. At the end of these iterates, all of the nodes will asymptotically converge to a value which is equal to the average of these original points. And what are the conditions, however? This happens if not only the row add up to 1, so that we perform convex combination, but also the columns add up to 1. And a simple choice, a very popular version of this randomized algorithm, is that nodes wake up at random, perform a pairwise exchange, they average the two values, they substitute that average with a new value. In this case, once again, these weights are time varying because the choice of pair that updates is random and have this particular structure where ei of t and ej of t are the coordinate vectors that point to the two vectors that do the pairwise exchange. And so this is the simple semantic of the algorithm. You initialize the expression to the original values that you want to average. You iteratively exchange the values and update with a convex combination of what the neighbors have sent. And after a T, capital T number of iterations, which is large enough, eventually the nodes converge to the average. And the rate of convergence is in fact exponential, even in the scenario where the matrix of weights switches are random. If we denote as W bar the expectation of the switching matrix, it is the first eigenvector of this matrix is going to be the all one vector with eigenvalue equal to 1. And what matters for the convergence, not surprisingly, is the second largest eigenvector of this random matrix. And as long as this number is less than 1, then the algorithm converges in expectation exponentially fast with a rate which is exactly that of the connectivity. Now, the question that may arise is why not choosing a constant matrix and repeat these updates synchronously? As I said, in a distributed environment, maintaining this type of coordination is in itself creating significant overhead. So one of the benefits of adopting these randomized techniques is that they are very forgiving in terms of failures, and they don't require coordination effort. It's interesting also to connect this parameter, the parameter that determines the rate of convergence, with notions that come from spectral graph theory. A particular choice for the matrix W can be done as follows. It can be the convex combination of the identity matrix with this parameter 1 minus gamma, what is called the Laplacian of the graph, which is a matrix defined as follows. The off-diagonal minus the weights, and the diagonal element is the sum of the weights. The Laplacian has always a 1, 0 eigenvalue, which correspond to the all one vector. And so the nullity is at least 1. But the nullity of the Laplacian is also tied to the number of connected components. So if the kernel of this matrix has more than 1, 0 eigenvector, is 2-dimensional or 3-dimensional, that means the graph is splintered in 2 or 3 or more components. The effect of this connectivity is shown in this picture. Here above you have synchronous updates with a certain matrix W bar, and the asynchronous update version is instead shown here that has in expectation the same exact set of weights. And you can see that obviously in the randomized approach, there is only one iterate at the time. These are pairwise exchanges, but the impact is pretty visible with lambda 2 equal 0.6. So the further is the second eigenvalue from 1, the faster is the convergence. In the limit, if lambda 2 becomes equal to 0, that actually means that the network is actually fully connected. And these are sample graphs. Among the sample graphs, who would think which one of these would lead to faster convergence? Well, once we understood the connection to spectral graph theory, it's clear that the more connected is the graph, for instance, this is an Erdős-Renyi graph, which is quite connected, the faster is the convergence. The cyclic graph has very slow convergence. A good compromise between the two are the small world graphs, that in spite of the sparsity, they have this randomized connection that connect these communities and speed up convergence significantly. Let's talk about big data analytics and particularly master-slave optimization. The most basic form of master-slave optimization, which is in fact the workhorse of machine learning today, is essentially a distributed version of gradient descent. And nowadays, we can tackle also constraint problems through a projection operator, and we can also handle non-smooth functions. So we tend to talk about the projective subgradient descent because oftentimes these problems are constrained and they have no smooth. But the more interesting versions of master-slave algorithms fall in two categories. One is mostly devoted to resource allocation problem, is the network utility maximization class of algorithms. And the second one instead is very popular in machine learning problems, is the alternating direction method of multipliers. The goal of the master-slave problem solution is to find a minimizer of the sum of objectives. And typically it is, the solution is computed at the slave. Now, master-slave architectures have benefited, been, as I said, the workhorse for cloud computing, thanks to two aspects. First of all, the introduction of distributed file systems that have become necessary when machines were occupied by terabytes of information, Hadoop in particular, was one of the first being employed. And that essentially led to a natural step. If the data is broken in several files, why not utilizing the machines where the data reside also to perform part of the computation? So the MapReduce functional programming model is exactly designed in this, with this philosophy. And the data that are multi-terabyte are divided in chunks over many servers that are the slave, and they perform what are called the map tasks, while the input, and these map tasks are the input to a reduced task that aggregate at the master level the information. This framework obviously is a programming framework which is more general. It helps to query data, parallelize other operations, but we are most interested in the parallel optimization via decomposition approaches. Now, the idea that one can map a decomposable problem solution in a gradient descent fashion onto a master-slave architecture is pretty straightforward, because then if we want to minimize the sum of functions, then the gradient is the sum of the gradients. And so the idea that we can decompose the sum of expressions into a master-slave algorithm comes immediately to mind, except that obviously, since the gradient descent is an iterative algorithm, in this case, we will have to perform several iterations. And so the slave task is to compute the gradient, and the master task is essentially to perform a descent step. For constraint problems, when X actually has to belong to a certain set, what we can use is the projection operator that projects X onto the closest point to the descent step that we have already made. And this is indicated by this particular operator. And for non-smooth problem, what we need to use is we need to replace the gradient with the so-called subgradient. This is a simple plot that shows what would be the subgradient of a non-differential function, this blue function, which is piecewise linear at point x0. Essentially here, there is an interval, which is the interval between the two slopes that we have on the left and right side of this point x0, and any point C within this interval is a valid value for the subgradient. And that concept can be generalized in n dimension. Now, let me make a popular example of the distributed gradient, which is federated learning. And the idea is, instead of bringing now the data on the cloud and use a MapReduce type of framework on the cloud, is to directly harness the computational power of mobile devices to compute the gradients and then perform simply the sum on the cloud. So on the client side, the nodes can actually utilize the model that they had previously, that they're utilizing for improved performance of the mobile device, calculate the gradient based on the new labels and do a gradient descent, and then this model is averaged on the cloud. Now, as we will see later on, one of the major differences between having a MapReduce task performed on the cloud versus having clients directly provide these updates is synchrony. So it's a highly asynchronous environment, and synchronizing these values along all the servers of the cloud that receive updates from the clients is actually a complicated task. And so typically what happens is there are several client updates, and then they're followed by one cloud update. Let me go to a different class of problem that leverages duality. And let me spend a few words on what we mean by duality. So if we have a problem which is now a minimization problem, I'm not looking necessarily at a decomposable problem here. We have an objective f of x we want to minimize subject to some constraint here. I put inequality constraint, it could be equality constraint. The Lagrangian of this problem has the following form, where lambda again is the vector of dual variable that correspond to this vector of constraints. We can define from the Lagrangian what is called the dual function. The dual function is a function of the dual variable lambda and corresponds to the infimum of the Lagrangian with respect to x parameterized by lambda. The dual problem consists of the maximization with respect to lambda of the dual function, subject to positivity constraint, non-negativity constraint for the dual variable, which are tied to the fact that this is an inequality constraint. So in general, the dual problem is always concave, so it has a unique solution. And the solution objectives, f star and gamma star of the two problems, are such that the difference between f star and gamma star is always non-negative.
And this difference is called the duality gap. When the original objective is convex and has strictly feasible solution, the duality gap is 0. And so the solutions that we obtain, X star and lambda star, by solving the primal and dual problem are the same. So not only duality has been used sometimes to solve more easily the problem, find approximation to the primal problem solution in the case of lack of convexity, but let's look at the impact that this idea has on network utility maximization, or for short NUM. Let's now cast the problem instead of the maximization of some utility as the minimization of some disutility. So the function fi are minus the utilities of the user. And now gamma is a dual function. The objective of the NUM, let's assume now, is separable. So we want, for instance, the sum of these utilities, or the sum of these disutilities, sorry, rather, to be minimized. And we have constraints on both the vectors xi, as well as we have coupling constraints. But importantly, the coupling constraints are also having this structure. Then the slave problem becomes one individual component. It's just a Lagrangian of one individual component of this problem. Since this is a sum constraint, there is only one vector of dual variable that correspond to this all constraint. But in this sum, we have a component fi and a component hi. And so the distributed primal dual implementation breaks the problem in the solution of the slave problem, right? The subproblem for an individual expression. And the master problem, which is again the maximization of the dual variable, which is a sum of dual variables. The iterative solution of the primal dual problem proceeds as follows. Each of the slaves solves its own local problem, and the master receives, based on the current value of the dual variable, iterate a new solution. And then the master problem, in general, cannot be easily solved directly. So the way it is done is iteratively through a gradient, in this case a gradient ascent, since this is a maximization. And so the expression of the update that the master does of the dual variable is shown in this expression. The previous value of the dual variable is changed by adding with the step size the gradient of the dual variable, the sum of these elements, which is nothing but the sum of the constraints evaluated at the new solution point. And this operator here that takes nothing but the positive part of this, so it's a projection essentially on the positive quadrant. The interpretation is the classic market interpretation, where the dual variables are the price, the customer adjusts its demand in response to the price until the market converges towards the socially optimum solution of maximizing the network utility. The dual methods are typically, as I said, applied to resource allocation problem, not to machine learning. But entering in the perspective of this decoupled dual optimization is what is important to understand also another class of problems, particularly ADMM. However, prior to that, it's also important to understand proximal methods. These methods are very popular in machine learning, and they also are an entryway to decomposing problems. For that, we need to define the proximal operator. The proximal operator is defined through this minimization. We have the objective of our optimization, f of x. To that, we add this quadratic term that is parameterized by this vector v. And the proximal operator for the function f is nothing but the minimum of this expression with respect to x. What is interesting about the proximal operator is that its application, its repeated application to an initial guess for x leads to also the solution of the optimum problem. And that is because in the solution of the minimization of f of x is a fixed point for the proximal operator. When we have a separable objective, there is this other useful property that if we can obviously break the argument, the vector b in blocks that correspond to the respective vectors of x. And the ith block of the proximal operator is nothing but the proximal operator of the subcomponent fi of the function. And this facts above explain how a lot of proximal methods work. So the first trick is that in some cases, certain functions are more easily amenable to applying the proximal operator because the proximal operator is simple, rather than performing a gradient descent because the function, for instance, is non-smooth. So let's say now instead of having a sum of many functions, that we have just a sum of f of x and g of x. The proximal gradient algorithm works as follows. It says first, do a gradient descent step on the function that is smooth and has the gradient. Let's say that that is f of x. And then do apply the proximal operator to the new evaluated point x to take care of the other term of the function g. And this is just really just a consequence of the fact that we explained below, but is also mixing and matching in a sense that f of x is actually a smooth function, while g of x is not. So the separability in a more general case, where we have g of x that, for instance, represents a regularization term or comes from a set of constraints that couple the problem, leads to this particular master-slave implementation. The slave can compute the gradient of the function fi, and the master can update, instead of just simply taking the sum of the gradients, can also take care of coupling constraints or regularizers by taking the proximal gradient of this new value, taking care of that term. The proximal operator, in fact, explains the projective gradient, because we can define a function g of x as the function that comes from the indicator function that says the function is 1 if x belongs to the set and 0 else. The proximal operator for this particular function g of x is nothing but the projection operator, and so that explains essentially as a special case the projective gradient, but it's obviously more general. One important example can be specialized from the case that we mentioned before. Here I am accumulating all the sum of terms in a single term, but here the lasso constraint is the solution of all the measurements, and so the proximal operator of this non-smooth term is actually has actually a very simple structure. It's called the soft thresholding structure, shown here, and this leads to the proximal gradient solution of lasso. And obviously, if we have a distributed environment, instead of having just one-step gradient descent on the entire matrix H, what we can do is, again, we can decompose it in the sum of terms. But to obtain from this idea of proximal gradient the alternating direction method of multipliers, it takes an additional trick. The additional trick is what is called often operator splitting. The operator splitting says if I have an objective which is the sum of, let's say again, just two functions, I can map this problem adding a new set of variable z and saying that I want to minimize with respect to x the sum of these two functions under the constraint that x equals z. Typically, this is solved adding a term that stabilizes and improves the convergence properties of the problem, which is this quadratic term. So instead of just calculating the Lagrangian, we calculate what is called the augmented Lagrangian, where rho is an arbitrary factor. Y here represents the dual variables which are associated with the consensus constraint. And so the way the ADMM algorithm works, it's again a primal dual method that assumes that we can alternate between optimizing an expression with respect to x, sorry, the expression of the augmented Lagrangian with respect to x, followed by the minimization with respect to z. And then once we have x and z, we can update the dual variable using simply the gradient method as shown here. Now, we can obviously also impose a proximal solution method for this. And rather than minimizing explicitly the Lagrangian as done here, we can actually utilize the proximal gradient of the function f and g with these arguments in order to update the values of x and z. And in this equation, I simplified the problem by defining this vector u, which is nothing but the dual variable normalized by rho, and I've incorporated rho as well in the definition of proximal gradient. ADMM is very interesting because in the problems that I've shown before, essentially there is a single vector x which appears in the objective. And if this objective is decomposable, as we said, we can kind of break it in master-slave tasks. But it has even more flexibility. Suppose I have two partitions of the vector x, and the one set of variables in x is in the set P, and the other one is the set Q. And let's denote the entries that correspond to these two sets with this specific notation. So the suffix is P sub I and Q sub I. And let's assume that we have a problem formulation where I can not only have a decomposable problem, but this decomposable problem pertains different variables in this set. And then we have this other component here that has to do with another set of variables. So in this case, it's clear that I can, once again, try to solve for the xi here. I'm looking at the proximal gradient solution, and solve for z, once again, using the proximal operator, and then update the dual variables. And the dual variables that I have to insert in these updates are the ones that correspond to the particular blocks of variables that are entailed. And again, I've used here the operator splitting trick to deal with that. So that means that these can be assigned essentially to different entities. So for instance, the slave could be taking care of this part of the operation, and they will be also performing the corresponding update once the master provides a new value for the remaining parts of the variables. This trick also explains a very popular implementation of the master-slave algorithm that tries to minimize with respect to a common x a sum of functions. This is done by, again, operator splitting, assuming that each of the functions depends on an independent variable, but then adding the consensus constraint over all the values of these variables. In this case, the slave task, here again, is solved with the proximal gradient, and instead of having only one x or one x within the set of x, like in the previous equation, it has the average across all nodes. And then the dual variable that correspond to the consensus constraint that pertains to this particular set of variables is updated once again, once this sum is obtained. And the sum can be updated essentially by the master as usual. So these computations are done at the slave level, and then the task of the master is very simple. It's just to add up all the terms. So in summary, we have explained these three algorithms: the distributed proximal gradient or subgradient, and the distributed primal dual decomposition, and the ADMM with consensus. And in all of them, if you notice, I've highlighted the presence of this sum. And this is crucial because here the master, in essence, in many cases, has had a function which was slightly more difficult than just adding terms. But that particular primitive is very interesting because in multi-agent optimization, that primitive is oftentimes just replaced by a sum over the neighboring nodes values. Let's start with the distributed subgradient optimization and then move on to the ADMM distributed optimization. Again, the goal is to obtain the global minimizer. The distributed subgradient optimization, the gradient step is replaced by this particular update that happens at each node. Instead of maintaining the previous value and descending on its own gradient, which is the only thing that each node has available, the node performs a convex combination, potentially with switching coefficient, of the neighboring value. And this matrix is typically also a stochastic matrix. It adds up to 1 both by row and by column. And then it descends on its own gradient. So the gradient is pushing essentially the solution towards the different direction that minimize the individual functions. But this convex combination is sort of the consensus term that's shown in the picture, makes the node come closer together relative to the points where they were finding each other. It is crucial for the convergence of this method that this step size vanishes, but not too fast. So it's non-summable, but it's square summable. And under this condition, it can be proven if the function have Lipschitz constant that they can converge exponentially. Very interesting is also the structure of the distributed ADMM problem, where the derivation is even more straightforward in a way. The idea is operator splitting, but instead of assuming that there has to be consensus across all the values in the network, the consensus is enforced only between neighboring nodes. As long as the network is strongly connected, there is a path between every node and every other node. This, in fact, is an equivalent requirement. And so, in this case, all the agents perform exactly the same task. They could minimize the Lagrangian or use the approximate gradient on their own individual function. But what they do is they put in the argument a convex combination that corresponds to essentially the constraints that they have with their own edge devices. And then the update of the dual variable u is performed as follows. It takes care also of the quadratic term in the augmented Lagrangian. So here is the set of two atoms vis-a-vis with each other, and you can see the parallelism between the two problems. Whenever we have a task that amounts to adding up all the variables, that is a master task, essentially what happens is that this is replaced by a sum over all neighbors. Now, is there any other network configuration in particular we should care about? I've been recently interested in combining these two architectures, the master-slave architecture and the multi-agent architecture, really motivated by the idea that the IoT devices generally, or also our mobile devices, don't talk to each other. So either because we have a fog computing layer, or because we acknowledge that the cloud itself is a distributed infrastructure, it might be convenient to look at the interaction at the higher level as a multi-agent system of servers, and still have an interaction which is a master-slave interaction with the IoT devices or mobile devices. And this would address the problem that in practice, fusing information from millions of edge devices cannot be done with a single server, and it's very complicated to arrange and coordinate even in the cloud. So that's why, for instance, federated averaging, the protocol that I described before, which tries to harness the capabilities of the edge devices to compute the gradient for training a neural network. This algorithm performs a lot of the gradient descent steps locally, losing optimality precisely for the need of updating not too often the cloud. If we assume that there is synchronization in the cloud and that amounts essentially to flooding the network, then essentially in terms of the network of servers, which is the set V, this will be an operation that has a quadratic cost. And if we indicate by delta of G the maximum degree of the cloud server network graph, what we have is that this ratio represents the ratio between the amount of time it will take to have each of the communications, assuming that V and V prime are for the edge devices cloud server, are indicating the average latency of this. And so as long as this is less than 1, it is advantageous to have a peer-to-peer type of structure in the communication of the server nodes as opposed to assuming that the cloud can synchronize all of its terminals. If we want to apply, if we can apply these problems, these can be also useful when we are seeking network coordination. But in general, if we are concerned with learning, what we can do is, as we already saw, each node itself has several data. The clients have some loss across the different clients of a single server, and then this other summation is adding up all the losses across each client for the model. And the way we can ensure the same solution exists is by simply splitting the consensus, once again utilizing the operator splitting trick used in ADMM. And so the ADMM hierarchical decomposition of the federated learning problem could work as follows. The client-server task would be pretty much that the client solves for the minimum of the augmented Lagrangian. It could also use a proximal operator, and the updates for the dual variables are as follows. And in here, the server has to pass to the client essentially the new model. So this actually, sorry, should be n. And the server task is essentially to average only with the neighbors the current states of the model that are obtained from its own subset of clients. As I mentioned, this architecture could be also useful in resource allocation problems. For instance, we have cloud runs. We want to also optimize the backhaul communications, not only the access channel. And so in this case, there may be server resources that we want to optimize, as well as the server resources, like, so this would be the communication channel between client and server, as well as the network resources that could be just one layer above and just pertain only the server variables. And here the Lagrangian can also be decomposed in sum of terms, and the idea is to utilize a decomposition that amounts to doing something similar to the primal dual decomposition, where there is a server client subproblem that is solved using the NUM algorithm. And then there is a network-wide problem where the function that we're trying to minimize is in fact the solution of the server client subproblem, is the decomposable solution of the server client subproblem. Let me now focus on the new solution of federated learning problem in the last few slides. This is the problem I showed you before, how you will have an ADMM hierarchical decomposition for distributed learning that fits this mixed multi-agent and master-slave architecture. Here we show a toy experiment, is the MNST database of handwritten digits. And we compare this with the federated averaging algorithm with two versions in both cases. In one case, the ADMM has a global constraint, so we have a single node, and that will be the benchmark. In the other case, instead, we have the mesh architecture. For federated averaging, we do a similar thing. We either have that the cloud correspond to a single node, or that the cloud is averaging all the models, synchronizing all the models over a mesh network. And in particular, for this implementation, we use TensorFlow on a mini data set with 1,000 training data, 5,000 test data. We have 100 clients, each with 10 private data. And we have 20 steps of the ADMM algorithm, which uses the Adam optimizer to solve the client-server problem. And the federated averaging instead uses 20 steps of subgradient descent for the local training. And under these conditions, as I said, federated averaging is actually suboptimal, while our method, our decomposition, will lead to an optimum solution. Now, of course, in neural network training, we cannot claim a global optimality, but for this particular algorithm, we actually have a convergence proof. And we utilize a network Shreni graph to, with the metropoly Hastings weighting approach to perform the algorithm over the mesh network of server. So you can see from this performance that all the methods reach a good classification accuracy. However, the ADMM over the mesh network reaches the benchmark of the ADMM centralized implementation, so with a single server instead of multiple servers in terms of communication rounds, while the federated averaging over a mesh network clearly has a loss, which is imputable, again, to the approximation that is made in making several iterations of the subgradient algorithm. The other interesting thing is that if you think about the composition, we can adapt this problem also when edge devices should not be trusted. So in an adversarial setting, we expect that some of the devices are providing bogus gradients or bogus updates to the master. And we will see that you can have a significant degradation in accuracy in federated averaging. And we see that depending on the number of clients that are attacked, we have more or less better performance. So here actually we have 5 out of 10 clients, and here our proposed method utilizes a more or less connected network. Here we have a single iteration with a certain set of neighbors. Here we have 5 iterations, and here we have 10 iterations, which is basically almost having converged to have an ADMM implementation with a single master. And the slight change here, instead of having consensus with the clients, we only have network consensus among the servers, but we regularize the problem so that we have to minimize also a new objective, which is not only consider the softmax entropy loss or whatever loss is for the training of the neural network, but also that we don't want to be too far from the model derived by the master. And once again, using the toolkit we have, is straightforward to derive the corresponding updates. We have a projecting gradient for the client-slave task, server task, and for the server task, we also have this simple 2 steps of subgradient descent. We have a theoretical result that proves that under a set of assumptions which are fairly standard on connectivity of the network, the convexity of the constraint and the fact that the function are bounded, in addition to having doubly stochastic weights, the algorithm actually does converge to a local minimum. And this is the experiment I showed you before. The test is similar to the one I had shown previously, except, as I said, there are 5 nodes that are sending random gradients. And so this degrades significantly the performance of federated averaging, but not of our algorithm. And this actually shows how different servers are affected. Obviously, the server that has the worst degradation is the server in yellow, which the influence of machine learning in the nodes is denoted by star. So here you can see the client and server 2 are not significantly, so the server is not significantly affected, but the client is affected, and all the clients of this server are unequally affected. But overall, because these are 2 servers that are directly or indirectly affected, so the 2 servers that are affected, the affected server and non-affected server converge to the same model, while the client in that particular subset that has the compromised node experience the degradation. In conclusion, what I would say is that we are at the point where we're going beyond a functional framework for computing in the cloud to a framework to allow computation to be performed more and more at the edge of the system. Multi-agent algorithms are yet to be widely deployed for fog computing. They are slower, but they are much less complicated to manage. They are fault tolerant, and they work around congestion because they look for network opportunities. It's important to look at hierarchical structures because edge devices do not talk with each other. And so it's important to acknowledge that there is still a master-slave component in this network, but then sort of free the structure of the communication in the layer of computation that occur above it. And finally, with the last example, I wanted to say that it's important also to embed in our distributed optimization formulation regularization terms or other terms that allow for not necessarily always consensus across all the network, but for relaxing that consensus, because we essentially don't want to blindly trust our devices. And with that, I conclude.
I want to thank you very much for your attention. Stay healthy, and I hope to see you soon.
Thank you, Anna. Thank you for your great talk. Yeah, it's a very systematic study on this topic from the mesh network, from the master-slave network, and then combined together. I think it's a very interesting topic. So we have some questions from audience. I can read it.
Yes.
Is there any rules for selecting the regularization parameter in the optimization problem, such as the parameters grammar in LASSO, and making it theoretically explicable that lead to the performance?
Any rules for selecting? Sorry, let me read it. Is there any rules for selecting the regularization parameter in the optimization problem? This is a very good question. Usually, this regularization coefficient that weights the weights the lasso term, for instance, or other regularizer, is chosen empirically. And typically is a trial and error. You can alternate on trying to optimize that parameter as well. But yes, I mean, it's a very good problem, very good question in the sense that typically this choice of the regularization coefficient is done empirically, which would require essentially maintaining in parallel potentially various objectives. We saw that the regularization term can be handled easily at the master level. And so you could potentially run in parallel multiple algorithms, but of course there would be a cost. So typically the answer is that it's more of a trial and error choice based on on the problem at hand. Sometimes if you consider the lasso problem as being derived from a prior on the data, then that prior could suggest a particular fitting of that lambda parameter, which will come from essentially a IID exponential distribution. But generally speaking, it's an arbitrary choice.
Mm-hmm.
Then there is another question, which is, do you think other problems such as noise, security, or trustworthiness can be accommodated within such sample-wise formulations? Absolutely. So noise is embedded in the expression. So these are all learning problems where essentially this expression fi of x embeds the noise impact. It's a loss. So that loss comes in many cases like a least square loss from a distribution assumptions on the observations. The security and trustworthiness, as I said, is handled by relaxing the consensus constraint. Another approach is actually to monitor the statistics of the messages that come from the edge devices. It's much more difficult to analyze because that would require to essentially exclude devices that have that are providing messages or gradients that are anomalous. And the slight complication is in not handling security by relaxing the consensus constraint and having a single formulation that handles all cases is essentially that when you cut off some of the nodes, some of the assumptions on the way you weight different nodes have to be readjusted. And so proving convergence is much more complicated for those scenarios. But empirically, these methods actually work pretty well. So the question is essentially more theoretical than it is practical. In fact, there is plenty of evidence, particularly in dual methods, that if the dual variables for particular nodes are very high, that means that those nodes are trying to push the network towards their solution, or if the gradients are far off from any, or the models are very different, that these are symptomatic of nodes that are essentially passing bogus gradients. So it's just a complication to handle the convergence proofs. Then another question is, do you consider the federation of edged components only or anywhere in the network? In my models, actually, there are only 2 layers, and these edge components, for me, in this model are the IoT devices or the mobile devices. So there is sort of a natural structural division where anywhere there is an IoT device, I'm assuming that there is a kind of a master-slave interaction, where at the layer above, I'm treating the system as a mesh network, and that is also sort of homogeneous. But you can match and mix all of these structures. So that was sort of the message. I didn't want to complicate enormously the notation, but what my point was that from this sort of prototypical primal dual method star master-slave network, models and the mesh network algorithms, you can actually sort of create all kind of complicated hierarchical structure. And particularly, I'm thinking about fog and cloud computing could be 2 different layers. And therefore, you could, layer and stack different type of interactions and have a more heterogeneous setup. I hope it.
Thank you, Anna, for your talk. I have another question regarding the communication rounds. How long does it take to compute them? And is there a difference between the algorithms that you've shown there in your figures?
Oh, definitely. So as I said, master-slave, so all of these in terms of rounds, if you could do the master-slave algorithm, that would be the faster in terms of communication rounds. But what is important to understand that doesn't reflect really the latency, because if you think about the fact that all of these edge devices will have to provide their update, right? So then you have to poll them, all of them. And so there is a single congestion point in terms of communications in the network, while naturally you're going to split also in the cloud the devices, and they are going to be queried by a different server in the cloud. So what my model, the second model was trying to represent is that this coordination that you need at the cloud level is going to cost you. And so saying that that's a single round may be misleading in terms of understanding what is the actual latency in terms of time. So the runtime is going to be actually higher per round. And so there is a trade-off here between the convergence of this mesh network type of architecture, which requires more rounds, but for each round, the runtime is much faster versus the master-slave type of vision of the world that essentially hides all the problem of essentially running all of these messages toward a single point or flooding all the servers with the same information.
So you've shown 500 rounds there in your figures, right? So how long does it take to run these 500 rounds, for example?
If you have a federated learning environment, it would be really up to the activation activity. So in federated learning, what typically happens is that you try to leverage times when the communication devices are charging. So in that case, essentially the main advantage is not having to wait for coordinating the network. So it is highly dependent on the particular activity from the edge devices. But I would say that what really matters is sort of the scale. So the advantage, as I try to convey, is the ratio between the degree of the network, so how many neighbors you contact, versus the size of the entire network. So it is hard to give it a number because, of course, it's highly dependent on the cloud environment. But the gain that you have is in the order of the ratio between the degree with which you communicate, which at most could be with one single server versus communicating with the entire set of servers, which is, I can scale to hundreds of servers for a cloud. So you can have a significant advantage. You can gain 1 or 2 orders of magnitude in terms of latency easily for a highly parallelized environment.
Okay, thank you.
Okay, thank you. Does anybody have more questions? So Andrew, do you have a question?
Yeah, so thanks, Anna, for the nice talk. I mean, I have a kind of more general question. It's related to this to the communication cost. So how would that affect the different methods? I mean, the amount of information that you need to transfer back and forth in the network, or if you
yeah, so this is related with the question that Martin made. So as I said, it depends highly on the environment. So clouds, you know, are really distributed, right? So if you are trying to handle everything on a single cluster, once again, it depends on how many workers are engaged in that activity. So if you organize it as a mesh network, then you can restrict the number of individuals you have to communicate. So communications are relatively fast. What really creates the bottleneck is handling a lot of messages creates congestion in the queue of each server. So by breaking it up, if you can, the connectivity of the network governs the rate of convergence in the meshed network environment.
So if you want, you can share your screen. So it's handy there.
Yeah, I haven't put up the slides, but if we can go, 1 second. 1 second, let me put up the slide so we can look at the comparison in communication rounds, which is what I showed you in the slide. Okay, let me share my screen. Okay, can everybody see?
Yeah, yes.
Okay, so let's go towards the end. So this comparison, as you can see, is, let's look at this other case where there are no. So you can see in communication rounds here, you roughly have, so this is kind of illustrating the suboptimality of federated averaging. So you can see that you roughly have the same number of communication rounds in this case, and it is because this is a relatively small network, right? Because it has 10 servers and it's fairly well connected, right? So if I instead go to hundreds of servers, then my network obviously naturally will be less connected. So if I keep connecting only 3 or 4 servers among each other over 100 servers, my number of communication rounds will degrade proportionally to that drop in connectivity. And so in this case, I probably will take, let's say, a factor 10 in drop in terms of performance. I will multiply my communication rounds by roughly the same loss that I have in algebraic connectivity. And so the question is, though, in order to synchronize 100 servers, this will require flooding the network, essentially. And so the comparison is how long does it require to flood the network versus communicate in each iterate with 10% of the servers. And so this is highly dependent on the way the workers communicate, but generally speaking, that would more than compensate the degradation that I have in communication round. So that has been my experience also in this small scale, that typically having to communicate, if I slow down, if I just reduce the connectivity in this network, I have a benefit in type of communication rounds, in the communication latency that more than compensates for the loss of connectivity, which in turn requires more communication rounds. So I don't know if I addressed the question. It's highly dependent on the configuration, but these are the trade-offs. Now, in the federated learning, there is another aspect, which is the intermittent nature of the clients. And for that, if I have an asynchronous scenario, then essentially each server can complete its task after having received a subset of the node updates. And so if I consider the fact that I'm only taking the minimum time latency update for this group of servers, then my rounds are actually ending faster simply because I'm not waiting for all the clients to update. So there are other trade-offs that appear when you have even a more distributed scenario with mobile devices.
Yes. Okay, great. Thank you.
Thank you.
Okay. So does anybody have more questions? Maybe Ami, do you have any question? No.
Okay.
Okay.
Well, thank you very much. It was a pleasure.
Thank you, Anna. So
all the best.
Thanks.
Thank you. All the best.
Before
Bye.
let's enjoy the Westlake video, Butterfly Love. So Laura, can you please play that video for us?
Yes.
Thank you very much.
That's a nice video, yeah.
Thank you.